Welcome to the Southern Blue Ridge Fire Learning Network and Fire Learning Network presentation that's also joined by the Consortium of Appalachian Fire Managers and Scientists. So we're really excited to hear today about monitoring results and fuel data, as well as seasonal fire effects from a team of scientists that have been working with us since we got going in 2006. Dr. Peter Bates with Western Carolina University has been working with a key partner in our network, North Carolina Wildlife Resources Commission, looking at fire effects since a few years before we got started. And when we were looking at for a protocol and a way that we could use consistently to track fire effects across 4 state regions on areas that were starting to put fire back on the ground, we reached out to Peter Bates, and that's where we got going, and we've really expanded our network tremendously. I'll let Pete talk about it, and then Pete was able to recruit additional great collaborators with Don Hagan and Adam Coates. So this is a great collaborative project, and I'll let it take. I'll let Pete take it from here. If you have any questions, please put them in the chat. We'll be answering them in the end, and Beth will announce the questions. So with that, we are recording the webinar, and we can share the recording later. So Don, it's Pete, it's all yours.
All right, well, thank you very much, Margaret, for that introduction, and welcome to everyone, and thanks for taking some time this afternoon to visit with us. You won't be able to see me because as I share the presentation, I have to have my camera off. But I think we're all, get my thing going. I think we're all interested here because we're interested in trying to understand fire effects. And we kind of have this continuum of observing what goes on field trips and things like that, just going out and seeing what happens after fire, kind of an informal, anecdotal way to check what's going on. And then we have experimentation, which is pretty well defined to test various hypotheses and so forth. But the big question comes in, where does monitoring fit in this continuum, if you will? And I think monitoring varies depending on the monitoring program. I think some monitoring programs are pretty robust and almost like research, and others are very informal. But for this presentation, I'm going to just put out there that I think the monitoring work that we're doing in the Southern Blue Ridge is what I call robust observation. So I think we have a pretty good idea of what's going on in terms of the trends within operational burn units. And again, that's a key point. When we do monitoring, we are doing operational burn units, not experimental treatments or things like that, but just going out and monitoring actual burns that take place. We cover a wide range of site and conditions, but our weakness is that we're probably limited somewhat in our ability to link cause and effect. And research, on the other hand, has much more control over conditions, a lot more statistical power, and a lot more ability for stronger inferences. So putting those together, I think, provides a powerful opportunity to come up with a more comprehensive understanding of how prescribed fire is affecting a region. So that's what we want to do today, is kind of combine some monitoring results with research results to see what kind of story we get. So our presentation outline is here, just so you know where we're going. We have a lot to get through. Hopefully we'll get through it quickly. But we're basically going to talk a little bit about the monitoring program, then some vegetative results, and then move into some fuels and a little bit of soils results. As Margaret mentioned, the Southern Blue Ridge has developed a pretty ambitious monitoring network. The backbone is 15 what we call demonstration burn units that are shown in blue on this map. They extend from Tennessee through North Carolina into Georgia and South Carolina. In addition, we've been able to build on that by having other partners or other landowners in the region kind of join our monitoring network by adopting similar protocols on their land. So we kind of are increasing the spread of our monitoring network. Today, we are going to be reporting on results from the 10 burn units that we've been monitoring that have completed, where we have data through 2 prescribed burns. And so those are shown in red on that map. It basically covers a time period that started about 2006 and goes through 2018. And the burn dates were 2007 to 2017. In terms of the monthly distribution, you can see that the burns happen whenever they can happen, as prescribed fires are. You can see that distribution there. The April is highlighted in yellow because some of these burns did occur in late yellow or late April, and depending on your definition, I'm sure that some of these probably were in early growing season. So we've had a lot of different kinds of burns that we're trying to monitor. The results I'm going to be presenting and kind of the basis of our monitoring is based on establishing permanent plots prior to the burns, and then remeasuring those same plots after each burn occurs. And so our typical setup is to have 15 plots inside the burn unit, and then we do establish 5 plots that will be unburned plots outside the burn unit. The caveat to that is those have to be located in areas that no one ever plans to burn in the future. And as a result, they end up in some pretty unique places that may or may not represent our burn units, but we try to squeeze those in where we can. In terms of locating the plots, it is a somewhat random process. We use Steve Simone's ecozone map for each of the burn units, and then we've identified target fire adapted communities that we're trying to monitor. So ahead of time, we just randomly pick locations where UTM grid lines intersect or halfway between UTM grid lines, and those are our plot centers for our plots. And then we'll go out and with a GPS and locate those locations for our plots. As I said, and what you'll see from me is our results are basically presented based on the sampling period. So we will present results for pre-burn, after the first burn, and after the second burn. And I do want to point out that we do our post-burn sampling during the second growing season after the burn, not immediately after the burn, but we wait until the second growing season to go in and remeasure. In terms of our analysis, again, we're looking at trends over time for those sampling periods. And the analysis we've done is basically to do ANOVAs for each population that we're interested in, if you will. So basically we've lumped all the burn unit or all the plots outside the burn unit together and kind of done ANOVAs on those, and we do the plots inside the burn unit. And we've also broken down our analysis by forest community type. So just a quick rundown on that. We, as everybody knows, the Southern Apps is a pretty diverse vegetative zone, and it makes a lot of sense to try to separate our results as best we can by forest community. So we basically have these 4 community types that follow an imperfect but probably somewhat real gradient from low moisture, nutrients, and elevation and latitude to higher of those elements. The yellow pine community is obviously dominated by yellow pine. Then we have 3 hardwood forest communities where the end members have been established pretty concretely. The drier end is dominated by chestnut oak forest. The wetter end is dominated by northern hardwood species. And then we kind of have the catch-all as mesic hardwood, which is everything that's in between. In terms of plot numbers, for these analyses, we have 175 plots that we will be talking about. They are not distributed evenly across all these communities, as you can see here. But in the burn units, we do have representation across all the different forest communities. So with that somewhat introduction, I'm going to talk a little bit now about the trends that we saw from the monitoring in terms of the overstory forest structure and the regeneration. So starting with that, I think it's really important to keep in mind, we always talk about this, but I'm not sure people really keep in the back of their mind how much our forests really are changing without fire. So here, here's an example, a picture from one of our plots that we took over an 8-year period. And you can see that we are definitely having continued growth and forest development in our unburned area. So, so when people talk about that, but as we analyze data and analyze trends, I think it's important to know that there is a trend that's happening in our unburned plots that we have to be aware of. In terms of trying to find the specific differences that with our data that we could tease these out, we didn't really find any significant differences between how the unburned plots were developing over time. Looking at the overstory on the left in this graph is basal area per acre. That wasn't a significant trend, although we had a 10 square foot increase in basal area, which I think is pretty important. Trees per acre stayed about the same. Looking at regeneration, again, in our unburned plots, we are seeing increases in regeneration. Looking at the species that regenerated the most or had the greatest increase, kind of those more mesic, more tolerant species. So again, not strong statistical support, but I'd say especially in our hardwood forest, it's important to recognize that we are having forest succession, mesification, whatever term you want to use, is happening. So now kind of switching to what our monitoring is telling us, and I'll give you the story before I give you the data. So basically looking at 2 burns on the forest overstory, and for our methodology, our forest overstory was live trees, and we measured down to 2 inches DBH. And again, it was only trees. So some of the findings that we saw that burning did reduce stem density, trees per acre, pretty significantly, but burning appeared to have a pretty minimal impact on basal area. Smaller diameter stems were most impacted by burning, which is understandable. We seem to find the greatest mortality in drier hardwood communities. I think it's really important to note that there was quite a bit of variation within burn units and within communities in the amount of mortality that we had. And if we talk about severity as the amount of overstory mortality, which we kind of developed an index based on that there's quite a bit of variability. So it's not a uniform response at all. And then the last one is that through 2 burns, we did see continued effects after the second burn. Obviously, it's very difficult for us to tease out whether that was a lag effect from the first burn or whether new effects from the second burn, but probably some combination of both. So now giving you some numbers, and again, these are just reinforcing what I talked about. I'll explain this first graph a little bit because you're going to see a lot of these, but basically they show the periods from pre-burn through second burn, and then if the ANOVA table results at the bottom, and then if things are significant at the 5% level, that's highlighted in yellow. So basically on the left, looking at overstory basal area, again, the trends show that the burns didn't have a significant decrease, but if you look at the trends, and this is as a monitor, we can maybe stretch things a little bit in terms of our inference, but again, it looks like basal area is increasing more in our unburned areas, and perhaps burning, even though it might not be significantly decreasing it, maybe it's stopping that process from happening. But on the right, trees per acre, that's where we do see significant reductions. Kind of breaking that down by forest community. And again, I'm not going to spend a lot of time on these, but again, we do see that different forest communities seem to respond differently. Our drier communities, the ones on the left, probably had more mortality. The northern hardwood, the one furthest to the right, probably the wettest forest community that we had less mortality in that forest community. So the size class was important. So again, I think it's pretty obvious.
If you want, I can bring the eggs after.
Okay, I guess we got eggs coming. So we can put in terms of the size, I think it's pretty obvious when people are out observing that smaller diameter stems are the most susceptible. And our results showed this, so we just lumped our diameters into into broad classes, pretty coarse classes. But the 2 to the 6 inch diameter on the left, this is only for the burned units where we had significant reductions. And we see that there's pretty strong evidence that in every forest community we're having a reduction in 2 to 6 inch stems. We get into the next larger class, 6 to 12 inches in diameter. Maybe some evidence, and probably we are having some mortality, especially after 2 burns extending into those larger size classes, but not as much. So clearly the early 2 burn results are most concentrated in those smaller diameter trees. And then this fire severity index, which we developed just as a way to get a handle on how much overstory mortality was occurring in each of our plots. We calculated this just as the average mortality in each of the 4 smallest size classes of trees that we measured, and then we took the average of those 4 values. And looking at those results after 2 burns, or after 1 burn on the left and 2 burns on the right, we do see that there is quite a bit of variability, and also that the severity or the cumulative overstory mortality seems to increase following that second burn. But looking at the yellow pine community after the 1 burn, we see that essentially the whole thing was in severity class 3 or less, which means we didn't have any plots where we lost more than 50% of our overstory, which much lower severity burns. As we get into some of the other communities, the xeric hardwood and the mesic hardwood, we start to see some high severity in some of the plots, probably indicating that those are the communities where even after 1 burn, we might be able to create some canopy gaps. Going over and looking after 2 burns on the right in that figure, we see much higher severities, much more greater percentage of our plots where we might have had greater than 75% stem mortality. So again, these effects, overstory effects, seem to accumulate and be cumulative after 2 burns. So that's the overstory story for me. Now I'm going to quickly jump to regeneration. Again, kind of telling you what I'm going to tell you before I tell you. A couple points I want to make is that forest regeneration, we define or we measure forest regeneration as regeneration that is greater than 1 foot tall. So we're not trying to go around and measure the tiny seedlings and so forth. So it has to be at least 1 foot tall and then up to 2 inches in diameter. And the other key point is when we measure regeneration, we count sprout clumps as a single plant. We don't count all the stems in the clump. But given that, we found that regeneration appeared to increase in both burned and unburned areas. Again, that's an important finding. It seemed to be primarily happening in our smallest height class or shortest height class, the 1 to 3 foot. Oak regeneration appeared to increase following 2 burns. Red maple regeneration seemed to remain constant. In our work out there, we noticed that there did seem to be some species that responded positively to burning, and those were black locust, black gum, and sassafras, and also other species that did seem to be set back by burning. And the biggest category of that was all of the pine species. The non-sprouters seem to be set back. So looking at those numbers kind of quickly. So this is, again, total regeneration in the unburned areas on the left, burned on the right. Again, not necessarily significant, but we did see regeneration increases, breaking that down by size class. So we had short regeneration on the left and tall regeneration on the right. Again, we'd had significant increases in both. So, I think this is really important for managers. And I hear more and more talk about, is it a regeneration issue we're having with some of these species, or is it a recruitment issue? And I think this is probably supporting that we are getting regeneration whether we burn or we don't burn, but whether or not we can get that regeneration up into the canopy is another question. So again, we got these high interest species. Everybody in our monitoring program wants to know what's going on with the oaks and what's going on with the red maple. So here they are. Our data show that we do seem to get a pulse of increase of oak regeneration after 2 burns. Red maple seems to be staying constant not changing much within our units. And again, if the trend, although not significant, but looking at the unburned, if the trend outside of burn units is for red maple to be increasing, the fact that red maple is staying constant might be a good thing. Again, the increasers, just 3 examples, and black gum, sassafras, and black locust look like they appear to respond to fire. These data are taken across all of our plots. I think if we focused in on just plots that had these species to begin with, we could probably refine this a little bit more, but it does look like some species do respond very positively to the burning. And then the decreaser are the pines. So we have found pretty universally that any pine regeneration that we have is pretty well knocked back. So with that, I was gonna go ahead and turn it over to Don and let him talk about his, and I control his slides. So Don, make sure I do that well.
All right, thanks, Pete. Can y'all hear me okay?
I can.
Okay. Well, I'm Don Hagan, and I'm an assistant professor and forest ecologist at Clemson University in South Carolina. And I'm just going to follow up with Pete, the stuff that Pete talked about, with some insights from some ongoing research in the region, because I think it can provide, I guess, some context and maybe some insights into some of the underlying mechanisms behind the mortality that we're seeing, behind the patterns that we're seeing in the monitoring data. And if you're like me, when you look at Pete's monitoring data, it's pretty neat that this has been going on long enough where we have sites that have multiple burns now, quite a few sites that have 2 burns. And of course, it kind of begs the question, we start to see some trends happening after 2 burns, but what happens if we continue to burn, right? What happens if we burn 3 times, 4 times? What happens if we implement maybe some other silvicultural practices on top of that burn regime? And so we're really fortunate here in the Southern Appalachian region that we have the Southern Appalachian Fire and Fire Surrogate Study Site. It's at the Green River Game Land in Western North Carolina. And you can see the map here, basically between Asheville and Greenville. And the Greenville, this Fire and Fire Surrogate Site was established in 2001. And Pete, you can go to the next slide. And 4 treatments were implemented, right? So we had an unburned control. We had a prescribed burn treatment where there were a total of 4 fires, 2003, 2006, 2012, and 2015. There was a mechanical treatment in 2002 and 2012. And then there was a combination treatment, the mechanical plus burn treatment. So each of those treatments was replicated 3 times. And then within each of those replicates, there was 10 vegetation plots. And we've collected vegetation data nearly every year since 2001 at this site. The original goal was A, to reduce fuels, and B, to restore that open woodland sort of historic condition. So one limitation of this research, compared to some of the stuff that Pete just talked about, is that it really just does focus on one community type. This is all predominantly oak, hickory dominated forests. But nonetheless, I think some of the insights here might apply to some of those other forest types as well. You want to go to the next one, Pete? So let's look at the control treatment. So just the general trends from 2001 to present in that control treatment. And it's pretty much exactly what Pete described. We saw a 17% increase in basal area during that 20-year period. So these forests, which were already dense, just got even denser. We did see some mortality. About 46 trees per hectare, so about 20 trees per acre died. And then just looking at some of the key species, our oak mortality was about 21%. So what that number means is that every single one of these trees was tagged at the beginning of the study. And then of those tagged trees at the beginning, 21% of our tagged oaks died. So we tagged every tree that was bigger than 10 centimeters in diameter was tagged. If you look at some of the competing trees, some of the more common competing trees with the oaks, yellow poplar, sourwood, red maple, and black gum, we're seeing mortality for those species ranging from 12 to 20%. So it appears, and these are just some data that are unpublished that I've just worked up over the last couple of days, it does appear that sort of your background rate of mortality is a bit higher for oaks than it is for some of their competing species. Can you click one time, Pete? And one more time. So those are the species, that's sort of your general trends in mortality. We also tag every tree that enters into that 10 centimeter diameter class, trees that get recruited to the overstory. And in the absence of fire in this control treatment, we saw 91.3 new trees per hectare recruited to the overstory. And these are your top 5 species, right? So we've got sourwood, red maple, black gum, mockernut hickory, and Fraser magnolia, right? So those are your top 5. Oaks obviously did not make it into the top 5. So I think collectively, when you look at these patterns, you see just what Pete talked about. These forests are changing and they appear to be shifting away from dominance by oaks. Let's go to the next one. We'll look at the burn treatment. So here's our prescribed fire treatment. Again, we had 4 fires over the course of 20 years, most recently in 2015. And if you look at those trends from 2001 to present, 4 fires had the effect of reducing basal area by about 4.2%. So as opposed to that substantial increase we saw in the absence of fire, we're seeing a fairly substantial decrease. We saw about 83 trees per acre die. And then our mortality for oaks jumped up a little bit to 25%. And our mortality for yellow poplar, sourwood, maple, red maple, and black gum ranged from 15 to 47%, depending on our species. So you introduce fire back into the system, and it might have killed a few oaks, but it appears to be killing some of those overstory competitors at maybe a faster rate. And you can click it real quick, Pete. One more time. And here's a similar graph that shows the top 5 species that have gotten recruited into the overstory over the course of the last 20 years. And it's mainly the same stuff, right? So sourwood is number 1. We've got red maple, we've got eastern white pine, black gum, but we did get 1 oak that made it into the top 5, and that's chestnut oak. So some differences in overstory recruitment. We didn't see nearly as many trees recruited to the overstory. It was only 32. And we do see 1 oak species making it into the overstory. Let's take a look at the mechanical treatment. Next slide. This mechanical treatment, which is repeated twice, it was just the chainsaw felling of small shrubs and small diameter trees. And what we saw with this treatment, it really didn't impact the overstory very much. We saw actually an increase in overstory basal area of 13.5%, comparable to what we saw in the control treatment. We saw some mortality, 73 trees per acre, per hectare. Oak mortality, they're in the mid-20s. And then yellow poplar, sourwood, red maple, and black gum, 15 to 21%, comparable to what we saw in the control treatment. So again, in the absence of fire, we're seeing that oaks might be dying off or being lost from the overstory at a faster rate than some of their competitors. And then if we look at the graph, you click the slide. Here's our top 5 species that got recruited into the overstory. And of course, sourwood, number 1, black gum, red maple, eastern white pine, and yellow poplar. All right, so that in the absence of fire, if all we're doing is a mechanical treatment to that mid-story, it's not tipping the competitive balance in favor of oaks. We're seeing a lot of those same species recruit to the overstory that we see if we just do nothing. Let's go to the next one, our final treatment. That combination treatment, mechanical plus prescribed fire, those trends, we saw a lot more change in basal area here, a 34.8% decrease in basal area. And I think what's happening there is because we added a lot more fuels to the equation, by felling a lot of those smaller stems, we saw some more extreme fire behavior. The fires were more intense and they were more effective at killing trees, including some of the larger overstory trees. We lost about 134 trees per acre and quite a few oaks also got killed. Oak mortality was 44%. But if you look at yellow poplar, sourwood, red maple, and black gum, their mortality was even greater, 60 to 67%. And let's look at the figure real quick. Here's our top 5 species that got recruited into the overstory under this treatment scenario. And of course, sourwood's number 1. Sourwood's number 1 no matter what you do. But our number 2 species was chestnut oak, right? So a more intensive treatment that results in more intense fire behavior does appear to promote the recruitment of oaks into the overstory. Yellow poplar was next, red maple after that, and then we have scarlet oak making it into the top 5. Now, we didn't have a whole lot of trees get recruited to the overstory, only about 12 trees per hectare. but it does appear that this more intensive treatment, multiple fires in combination with some mechanical treatment, might be what it takes to shift these forests back maybe in the direction that we want them to go. All right, next slide. But that's just the overstory. What about the regeneration layer? And I should add that those overstory results aren't published yet. We're working on that and doing some more refined analyses to tease out those trends. But let's look at the regeneration data, looking at some stuff that has been published. This is from my student, Emily Oakman. She did some work looking at the understory in these sites, looking how it changed from 2001 to 2016. We've got oak regeneration there on the left. And here we're talking about oak stems that are breast height or lower. It's a small advanced regeneration, basically. And as you see, really across the board, you know, we're getting quite a lot of oak regeneration. In all 4 treatments, there's more oak regeneration at the end of the study than there was at the beginning. But those 2 at the top, that's the mechanical plus burn treatment, and then the burn treatment appear to get even more than the other 2 treatments when it comes to oak regeneration. And of course, that mechanical plus burn treatment, like we just saw, also creates the condition that allows some of these oaks to maybe recruit into the overstory. There on the right, I've got mesic hardwoods or mesophytic hardwoods. I did lump red maple in with this, and we could debate whether or not that's appropriate. But one thing we do need to be cautious about is if you look at that one line that increased pretty dramatically from 2001 to 2016, that was the burn treatment, right? So we see a lot of regeneration of these mesic hardwoods, namely red maple, when we just burn, even if we burn 4 times. We go to the next one. So I should add, though, that all of those fires were in the dormant season. So they were generally in that sort of January to March timeframe, which is when we typically burn in the Southern Appalachian region. But I do have another study going on that's not part of the Fire and Fire Surrogate Study project that looks at fire seasonality, right? So what happens if we burn, say, in late April versus January, February, or March? And we looked at some of the same metrics that we've looked at with the Fire and Fire Surrogate Study treatment or design, and with a fairly similar study design. So I've got 3 treatments. I have an unburned control, I have a dormant season burn treatment, and then I have a growing season burn treatment replicated 3 times in Northeast Georgia and then in the upstate of South Carolina. And I don't have time to go into too many results, but you can go to the next slide. One thing that we noticed, and I figure a picture is just as valuable as some actual data, is that the fire behavior in those early growing season burns was different. It was more intense than what we saw in the dormant season. It was actually quite similar to what we saw at the Fire and Fire Surrogate Study site in that mechanical plus burn treatment. So the fire was hotter, it did more damage to the canopy, and throughout these studies, throughout these units, there are sites that look like this, where the fire actually succeeded in creating some gaps in the canopy, either by killing trees completely or damaging their canopies sufficiently to let more light come down to the ground. So this is that kind of scenario that can encourage those oaks that were quite abundant in the understory in this study as well to potentially recruit into the overstory. We go to the next slide. The biggest impacts of these fires, whether we're talking about the Fire and Fire Surrogate Study study or the seasonality study, seems like the biggest impacts that we see are on the mid-story, not so much the overstory or the understory. And this is from the seasonality study. You can see what's going on with the control treatment, the unburned control, and then also our dormant season burns and our growing season burns for trees and shrubs in various size classes. And what you can see here is that in general, those growing season burns were more effective at reducing the density of small woody stems in the mid-story, possibly just because the fire was more intense. We go to the next one. And we've got all sorts of species-specific responses we can look at. One species that was really appeared to be impacted by growing season burns more so than dormant season burns was eastern white pine. We're getting a lot of eastern white pine recruitment. We saw that at Green River, at that Fire and Fire Surrogate Study site. And those growing season burns appear to be more effective at killing those young eastern white pines. If I showed you the graph for red maple, you see that it's also fairly similar. Those small established red maples, you tend to get more of them if you burn in the dormant season, but you get less of them if you burn in the growing season. Go to the next slide. So just some takeaways before we get on into the fuels. Just like Pete said, the effects of individual prescribed fires are modest, but they are cumulative. So a lot of the mortality that you see is delayed, but a lot of these trees eventually do die. You know, we're basically, when you look at these unburned units, you can, over the course of 15 or 20 years, you can see that process of mesification in action. And those repeated fires maybe didn't stop it, but they appeared to at least slow it a little bit. We didn't see the forest getting quite as dense, and we didn't see as much recruitment of those mesophytic trees into the overstory. And those additional treatments, whether it's mechanical treatments and fire or burning in different seasons, may help expedite the restoration process. So as we think about maybe continuing the monitoring program on into the future, it would be interesting to maybe add even more of these growing season treatments. I know Pete already has some of them, just to see how these patterns maybe hold true in different forest types across the region. So that's all I've got. I believe Pete's next. He's going to talk about fuels.
All right, well, thanks, Don. So yeah, back to me to talk a little bit about our monitoring results on fuels, and then I'll throw it to Adam. So again, to start with the story, so a couple points just to keep in mind that our fuels monitoring is done with the rest of our monitoring. So this is not immediate post-burn. We're measuring the fuels during the second growing season after the burn. So we're not directly measuring consumption. Given that, what are we finding? Well, it looks like we might be reducing litter thickness by prescribed burning slightly, at least as represented 2 years after the burn. We have less evidence that we're impacting the duff layer. And in terms of the woody fuels, kind of a mixed bag there. I'm glad we have Adam here to explain it all to us. But the 1 hour fuels seem to vary quite a bit. We did in our monitoring data seem to see a definite pulse or increase in both 10-hour and 100-hour fuels after the second burn. And then our 1,000-hour fuels remain largely unchanged. So just kind of looking quickly through the numbers that go with that. This is litter thickness on the left, is comparing or looking at our unburned areas versus our burned areas. And then on the right is looking at the different forest communities. And again, indication, good evidence that we are reducing the litter thickness after both 1 and 2 burns. Not a drastic reduction. And again, who knows, if we stop burning, the litter probably would accumulate quite quickly after that, but this is what we're seeing for litter. Looking at duff, overall, not much of an impact on duff. Again, that trend in the unburned showing it was significant, but again, the depth isn't that great, but it's just, we don't seem to be having that much impact on duff, except maybe in some of the very driest communities, either through fire getting into the duff or just less litter to make duff, but overall not much of an impact on duff. Looking at the woody fuels, 1 hour, if we look overall at our burned units, we see maybe a little bit of a decrease, but looking at the individual communities, again, it's kind of a mixed bag. It's not that hard to kind of come up with explanations for all these things that might be plausible, but we need research to really help us understand what's going on with this. And then the 10 hours and the 100 hours both kind of had this pattern of, after the second burn, seeing an increase across most of our sites. Now switch over to the 100 hours, see that same thing. So kind of an interesting trend there for sure. And then finally, the 1,000 hours, didn't really see much of a change in 1,000-hour fuels. So with that monitoring results, I'm gonna get ready to turn it over to Adam. And Adam, as you heard, I'm gonna have to switch for you as well. So just let me know when you're ready to switch. And without further ado, Here you go, Adam.
Sounds good. Sounds great. Well, appreciate you all being a part of the webinar. And I'm Adam Coates. I'm the assistant professor of fire ecology at Virginia Tech. And I'm excited to talk a little bit about fuels things, really highlighting a couple of things that Pete pointed out from the monitoring data is you do see these trends of some increases in some fuel sizes and fuel types as after burning. And also like some changes that would be occurring also in the unburned control plots as well. And so kind of highlighting with these two studies I want to talk about that we've recently done here at Virginia Tech, like fuels are changing even in the unburned locations. And then the story with the burn plots is not necessarily universal, that all fuel sizes and all fuel types across the board are going to be reduced. It might not even be that they're reduced after the first burn, but you might see gradual progressions in some reductions as additional burns are included beyond the first like single entry, and particularly if it's like just dormant season burning as well. So a couple of these studies to highlight, this one we just recently had published in Forest Ecology and Management. I'm looking at two watersheds. It's a watershed scale study that really began in the 1960s with two paired watersheds being set up to largely look at water quality. But as a result, so many other ecosystem components and properties have been looked at and evaluated as well, including soils. And so I'm going to bring up some soils information here as well, because we know, and I think you'll see from this study, that what's happening with what's being burned and what is actually remains in the soil and what's going into the soil, they're connected. And some of our attribution to direct fire effects might be a little misleading if we're not also looking at vegetative effects as well. So with this study, there's two watersheds. Watershed 80, I'm going to be referring to it as an unmanaged watershed. Since the 60s, it has not been managed, actively managed. The passive management style is what's been done. So basically no activities were done. Even after Hurricane Hugo in 1989, no salvage logging and no harvesting was done there. In watershed 77, that's about 2 kilometers or so away from watershed 80, a lot of things have been done, including prescribed fire, understory mastication, mowing. And so as you can imagine, as we're going to show in a couple of slides, the vegetation composition looks different. So Pete, if you'll click the next slide, please. So there on the left, you can see the managed watershed, reduction in hardwood basal area, something that you're going to see, more grassy understory that's present. And some of the lack of hardwood regeneration is going to be present in that managed watershed, again, there on the left. In the unmanaged watershed, something that you'll see pretty characteristically is there's an abundance of 1,000-hour fuels that were there, a lot more litter cover as well. And so we wanted to compare just the differences and the changes from top to bottom in the overstory of the fuel complex, and then also what was actually in the soil. So next slide, please. So to look at all of these, there's a good bit of information in that table, but again, we're just kind of going from top to bottom, from overstory all the way down into the soil. So to start with overstory, we saw in the basal area for the unmanaged watershed, you had a greater total and hardwood basal area in the unmanaged watershed. In the managed watershed, you had greater softwood basal area, largely dominated by loblolly pine. For fuels, looking at both masses and depths, duff mass and depth was greater in the unmanaged watershed. 1 hour fuel mass, rotten 1,000-hour fuels, and then fuel bed height. If you're just measuring using Brown's transects, if you're familiar with that technique, we were using 3 measurements along 3 separate transects to come up with a total of 9 measurements, where you're literally just looking for the total height of the down and dead woody debris, and that was greater on the unmanaged watershed. Something similar that we saw in the monitoring plots, as you see that 10-hour fuel mass actually was increased on the managed watershed that did have more prescribed fire in it. And this is over the course of 50 years of these management practices being included, and about 4 prescribed fires that were used as well. So next slide, please. To track into that, to look at litter and duff and kind of think about the chemistry that was present there, what you'll see is that for all of the properties we measured, this is pH, phosphorus, calcium, magnesium, potassium, nitrogen, and carbon. For everything but carbon, in both the litter and duff, the unmanaged watershed had higher quantities of those soil chemicals. If you'll go to the next slide, Pete, the interesting thing was that if you looked at the 10-centimeter soil depth and also at 10 to 20 centimeters, the differences for phosphorus and calcium were maintained at both soil depths. The others were kind of diluted and we didn't find statistical differences there. But kind of the take-home message of that was, well, if we're seeing some of these differences in heavy clay ultrasols, where you're seeing that phosphorus and calcium are being different, a lot of that can be related back to the differences we saw in the litter and duff. And so fire was directly, causing changes in the overstory composition, which was then linked to these changes in soils. With many other studies of soils and ultrasols, what you weren't finding was changes in these soil chemicals and in these properties. I mean, a lot of that was related to kind of these nondescript or, non-significant changes in overstory composition. So really kind of understanding what's actually going on with the fuels is pretty important to what's actually going to be related to the soil chemistry. And you can't dissect that and take that away from what's actually happening in the overstory as well. So if you click the next slide, please. Kind of the takeaways from this study, again, where you can see in the upper image there is the unmanaged watershed, the lower image is the managed watershed. The total fuel loads did not change in these watersheds. If you were to compare just total masses of fuels, they would be the same, statistically significant. There would not be significant differences between the two. But what we did see is these different components of the fuel beds change. And of course, something that I didn't actually measure between these two watersheds was the actual mass of the grasses that was there and other live vegetation that might be included in the understory that might also, it really would have led to even kind of this more, you would have gone in the same direction of having non-significant differences between total fuel masses if we had included that grass component in the managed watershed. So the total fuel loads didn't change, but you did have these altered compositions and arrangement of fuels. And so ultimately, if there were prescribed fires that were included in both sites, and ultimately if you had a wildfire occur in both stands, kind of what we're talking about in that research article that we produced from this research, was that you would have inherently different fire behavior. Particularly with those 1,000-hour fuels, maybe even having less opportunity for some of the fire behavior that you might actually want to have occur. You might have that impaired by just that increased amount of 1,000-hour fuels if fuel moisture and soil moisture were elevated. Indirectly, fire altered forest composition, which then led to changes in soil chemistry. The management priorities dictated the efficacy of management in these watersheds. So depending on what you're really wanting to derive from both of these management techniques, might help guide you into if they're appropriate or not. And that could include water quality, wildlife habitat, and hazardous fuel load maintenance. What you're really trying to get off of these properties might help dictate which management scheme would best fit your priorities there. So to go to a second study, Pete, if you could click the next slide, please. This one has occurred in Great Smoky Mountains National Park, and I'm still doing a lot of the data analysis on this. Rob Klein, who joined the call, this is actually some work I've been able to partner with him on at the park in this Great Smoky Mountains National Park. So click next slide, please. Some potential management concerns that exist in this park and other locations in the Southern Appalachians, as Don had alluded to and as Pete had alluded to as well, is just this shift in vegetative composition and structure. Largely, as you can see in this image here, a presence and abundance of ericaceous shrubs actually expanding kind of on the southern and western facing slopes and actually moving higher into upward slope positions, causing differences and an inability to regenerate the species that we most desire. Changes in fuels will be present as a result of that. And then actually thinking in the last 20 to 30 years, the presence of hemlock woolly adelgid and the effects on forest composition that might occur as a result of hemlock actually dying out. And also substantial wildfire hazard that was present as evidenced in the 2016 Chimney Tops 2 incident. So next slide, please. So what we did is in 2003, 2004, about 700 different plots were sampled across the Southeast. Some work has been published on that as well. And what we wanted to do is go back to those plots that were included in that larger study and actually look at fuels changes that had occurred in the last 16 to 17 years. We were able to do this work in 2019. We went back to about 50 plots and we actually only included 40 of those in the analysis here, just based on trying to understand where we're in the exact same locations as the original researchers were in when they collected this data. So next slide, please. So got a lot of information here. We're basically breaking down the fuel beds once again. I'm looking at, and on the left, we included all the plots that were measured, all 40. In the table on the right, what we did was looking at some of the plots. If we really wanted to get some of the questions about eastern hemlock, we wanted to do a separate analysis, just thinking about, okay, was hemlock present in both sampling periods between 2003 and 2004, and then in 2019? Like, if we wanted to talk about hemlock, were we seeing hemlock in both stands in both years? And so we separated those hemlock plots out, where we knew that there was at least some presence of those, even if they were standing and dead in both years. And so if you'll see there with the all plots, there are definitely differences in some of the fuel sizes and fuel classes. I think the most profound thing to not see for all the plots is that there wasn't a difference in the total amount of woody fuels that were there. If you look at the hemlock only plots, if you see to the right there, there was a difference in the total amount of fuels, and that amount in 2019 was actually greater than it was in 2003 to 2004. Next slide, please. Can we go ahead and get the next slide, please? Yeah, so thinking about some of the results that we had there, I became pretty curious. And I'll show in the last slide, we recently came up with a fuel guide, a photo guide for the Southern Appalachians, and thinking through just what might be occurring with some of these changes, if there happen to be any differences that were related to aspect and elevation. Is there any difference that might be occurring also as you get to these different site types and different site qualities that might be present? So real simple way of doing this, we kind of separated them into northeastern, southwestern facing slopes, and then high elevation and low elevation. And if you'll see on the left there, this is a principal components analysis. The 1, 2, and 4 is represented by these different aspect and elevation combinations. Kind of this higher elevation northeastern facing slopes, it kind of separates itself into its own quadrant, separate from the 1, 2, and 4. And you can see in that quadrant, if you actually take that number 3, transfer it over to the right-hand side, you can see that more of our kind of heavier fuel components are there to the right. That includes live basal areas there, 1 hour fuels, fine fuels, which is the 1, 10, and 100 hour fuels added together, dead eastern hemlock, the litter averages kind of pulling that direction. If you'll click the next slide, Pete, we separated that out and actually did the numbers on that to see just that principal components analysis gives you a little bit of an idea. Are there any kind of trends that are present? And then to actually look at the statistics on that, what we really pulled out was there were some differences in 1 hour fuels, live basal area, total basal area, and then the total amount of eastern hemlock dead basal area when you separate out by aspect and elevation. One thing that's curious to me is we had, like I said, 40 plots that were included in that type of analysis. And as you see those break out to be about 9 to 12 plots per aspect elevation combination there. So I wonder, if there would be a more distinct separation if more plots were included. In those compositions. I think you do see that there are some noteworthy trends there, especially with like live basal area. It actually, the difference in 2019 live basal area was higher on the northeast high elevation positions, whereas all others, there were actually a decrease over time. And so that's a kind of a noteworthy trend where at least there was some amount of difference in the positive and negative direction. And I think could be explored more with looking at different data sets and maybe even collecting some different plots from this particular study. So if you'll click the next slide, please. So some takeaways from that study, I think the more pronounced takeaways is that going back to these plots nearly killed some of our technicians. So the image on the left is one of the technicians who was really hard worker, really did a good job, but he admitted at the end, like, this work about killed me going back to some of these plots and trying to identify them with using Brown's transects was the technique that we did, trying to get to the exact places where these measurements were made in 2003, 2004, proved pretty tricky in pretty difficult terrain to navigate. So my hat's off to them for working on this project. So there were changes that were noted with the fuel components there. Some of those changes were more pronounced on plots containing eastern hemlock that I think we could explore more with kind of investigating that further. I think evidence suggests some of those changes were impacted by aspect and elevation. We were seeing some fuel changes there, maybe not as pronounced as we would have expected and as I kind of hypothesized, but I think there were some changes that were there that could continue to be explored with looking at the data a little bit further. Shrub expansion, as I might have assumed, was not as pronounced over the time period in these particular plots. Not to imply that that's not an issue in other locations throughout the Southern Appalachians and Central Appalachians, but we just didn't see it in these particular plots. So click the next slide, Pete. That's all I've got on the fuels after this slide. So I think from both of these studies and thinking about the things that Pete talked about as well, prescribed fire does not universally equal fuel reduction of all types. Differences in single entries and repeated ignitions, as you know, some of these single entry dormant season ignitions, you might not see these massive reductions of all fuel components across, especially when you're comparing unburned units to burned units. You do see more changes, I think more drastic changes, particularly in the litter and the duff scenarios when you have repeated ignitions. And I think we've seen that in studies from the Appalachians and the coastal plain. The desired fuel composition, arrangement, and availability of fuels, must be considered pre and post fire, I think, to better understand what's actually happening and potential fuel changes as fire is included on the landscape. There's inherent complexity present when considering different topographic positions and features. Fuels change with and without prescribed fire. We could definitely see that in the study on the coastal plain where we had long-standing damage from Hurricane Hugo that was included, not related to prescribed fire, but it translates to other landscapes with other disturbances that aren't just fire related. I think continued work is needed to improve our fuel estimation techniques, which would include the Brown's transect method that we've done for years and years now, both in western landscapes and in eastern landscapes. And we're experimenting more now with terrestrial LiDAR and other imaging techniques that I think will have some opportunities and provide some advantages, especially in repeated ignitions when you have multiple burns, to look at different fuel components. Thinking about forest floor inventories and actually beginning to kind of take what we did with the fuel masses, the study on the Santee, thinking about how that relationship between chemical components, thinking about nitrogen, thinking about calcium, some information would suggest that as we change fuel components, even as litter components change, as you've changed overstory dynamics, we might be changing the masses of litter and duff, but we also might be changing the flammability of those components. And some of that I think is related to the chemistry that's associated with these different species. Just as their leaves look different to us physically, I think those relate to chemical changes as well. And I think our study on the Santee kind of explored that. And I'd like to ask that question more, I think, with some of our Appalachian studies as well. So to ring the bell of soils, don't forget about soil impacts, because they may both reflect our restoration effectiveness and also impact restoration effectiveness. Thinking about nitrogen dynamics and other inherent nutrient requirements that some species would need both in the overstory and the understory. So that's all I have for the fuels part. Thanks for tuning in for that.
Okay, that's thanks, Adam. Let me get that. That's kind of the end of it. I know we had a lot to go through there, so I guess Beth, you were going to take it from here in terms of if we have time for questions or how you want to handle that.
Sure. Do we have time for questions? We don't currently have any in the chat box.
I have one.
Okay, one just showed up. Great.
Two.
So Pete, was your presentation based on a published article? It says those results showed no decrease in duff with fire, while the study that Adam went over did show a decrease. Would that be due to site variability, do you think?
Well, no, I mean, ours is not, we haven't published the monitoring results. So, I mean, they are what they were. I mean, the fuels and the duff, as you know, Beth, it's kind of hard to figure out what's going on with that one. And in some cases, we may have gotten into the duff with the prescribed fires. It doesn't look like that happened very often. So, you know, determining what the mechanism might be for reductions of duff is something that, you know, is hard for us to tease out. And plus the reality is when we're measuring duff and whether it rained or how humid it is and all those things kind of influence things as well. So I'll kind of defer to Adam and his results on duff dynamics following fire.
Yeah, what we did see in the CNT study that was published in Forest Ecology and Management, like we did see differences in depths and masses there. And again, that's 50 years, frequent prescribed fire.
And did you have any follow-up on that then?
Yeah, can you guys hear me? Hello?
Yes. Yeah, go ahead.
Okay, good, excellent. Yeah, so what I was saying, with the CNT study that was published in Forest Ecology and Management, like we did see some differences in duct depth, and I think those are largely a result of repeated ignitions, some that included actually some significant ignitions where you had higher fire intensity and higher fire severity, particularly after they had done some mastication and some mowing and allowed those fuels to cure. So you've had reductions of duct there, I think, largely as a result of those higher intensities and also the repeated ignitions. With the Smoky study, what we saw was that duct depth actually was increasing over time. And I think that could be expected. One thing I kind of relate back to with the Brown's transects, and Pete alluded to it there a little bit, is if you have multiple people actually doing these measurements over time, it's simply an ocular estimation of what you think duct depth is and where you would distinguish between litter depth and duct depth. And that can very much be, the beauty is in the eye of the beholder as where you call that distinction. So a lot of the studies that I've done, I'm the person that's following up from one year to the next, before fire and after fire. I'm doing all those measurements just to make sure like the error is coming from me in that regard. So I think there can be some number difference on that. And some studies that I've done recently, we've related everything back to, okay, let's just take the total depth of the forest floor and include both litter and duff. That way you're kind of accounting for some of that error. The only problem with that is, as you would know, and as you're seeing in some specific questions we get from managers a lot, is what is specifically that number on the duff and are we affecting it? Because cutting it into it too quickly can drastically affect overstory dynamics when you may or may not want that to happen by killing out feeder roots when you're actually burning from the overstory trees. So I think some of the story is our dormant season burns, especially with single entries. And even after that second entry, if you're really doing dormant season burns that have lower intensity and have lower severity, and you're actually trying not to burn a lot of the duff, I think we're showing that we're not doing that in a lot of cases. And I think that could be related to some of our results. You can judge that as good or bad. I'm just making the statement in that regard of, I think that can be related there. And might be able to shift some of the results if we want to have more significant impacts on the duff. I think actually targeting some drier conditions, not completely dry or anything like that, but having some differences in our prescriptions might lead to some more significant differences in duff dynamics after that first and second burn in particular.
Great, thanks. It does look like we're starting to get questions come in, but unfortunately we're actually at the top of the hour or a minute or two past. So out of respect for everyone's time, we are going to cut it off now. But I know that we can certainly have lots of conversation about this in future webinars and FLN workshops and the like. So I'll just say, unfortunately, we don't have time for other questions. But Margaret, would you like some closing thoughts other than thank you to everyone?
I think it would be great. If you have additional questions you would like answered, if you can send them to me, I'll put my email address in the chat, then I'll be happy to relate them. Will that be okay?
Yeah, I think that would be great. And I know that we could also all go direct with the presenters as
Yes.
well. So yeah, great conversation. Thank you so much for all of the information from the three presenters. We really appreciate your time, and we look forward to hearing more results as time goes on.